Hi everyone, welcome to the lecture series on structural dynamics. So this lecture on introduction to the dynamics, part 1, which explains the little bit of the basics, very fundamental of the dynamics, which is like type of loading or what is the structural dynamics, what is the type of analysis meaning by the static versus dynamic. Then we talk about the degrees of freedom. Then go to the dynamic equilibrium equations. Okay, the remaining topics will be the part 2 of the this introduction. So now let us see the sources of dynamic loads. From where we find the dynamic loads. So if you look at carefully, the wind will have a fluctuating component called gust wind, gust factor, which is the vibrating part of structure to the structure. It is not simply a static load onto the structure. Second is the earthquake load, is the dynamic load, which is time variant. Then the ocean waves onto a jetty or a ship structure or a berth structure is a dynamic loading. Then the rotating machines loading onto the foundation is the again dynamic loading. Then we have a vehicular movement onto the bridge is again dynamic loading. The amount is different, location is different, time is different, and the train over a time the load changes on the bridge. So this is the dynamic loads onto the structure. Not only that, we have like the pile driving, when the pile being drilled, so that causes vibration onto the ground, the neighboring structures will experience the vibration. Then we can also see the metros, when train moves, the nearest structure undergo the vibrations. Then the blast operation carries out the quarry, which causes the vibration onto the structure. So these are the sources of dynamic loads onto the structures. We need to understand the loading type, the duration of the loading, the amount of loading, dynamic loading, then its travel path, the amount of dampness by the time it reaches the structure. These are all very important to understand. Now, if you look at the analysis type, one is we discussed like static analysis, and there is something called dynamic analysis. So as far as the applied force is concerned, how do I separate a static analysis to the dynamic analysis? That means the applied load for a static analysis, the load is constant. This load is a constant. Wherever it is a constant load. Right? Whereas in the dynamic analysis, the load is varying with the time. At this point of location, at this point, the one time is 10 Newton, another time 20 Newton, another 30 Newton, another time maybe 5 Newton. The load is not constant during the life of structure. Okay? The second is the magnitude of the force and the direction and the point of loading are all constant here over a time. How much amount? Direction. That is downward force is going to be downward force rest of the life. And then location of the here or here. But whereas in the dynamic analysis, the amount, the magnitude, the direction and the point of loading will change. Then we can call this analysis to be a dynamic analysis. So any one of the above or in combination is not constant, then it is called dynamic analysis. Now let us look at from the point of view of a response of the structure. Once the load is applied, whether from the response I can understand whether is it the dynamic analysis required or static analysis required. So once the load is applied, the beam gets deflected. The response, that is the deflection, is going to be same throughout the time. Right? The deflection remains same. We assume the deflection is same. It is not varying with the time. Then we call it as static analysis. Right? So there is no velocity of the system, there is no acceleration. But when it comes to dynamic analysis, the response, let us say first of the response is my displacement response. That means deflection of the cantilever beam will change over a time. This is the time axis, and displacement will have a different. Then the velocity of, again this is the velocity of the response structure will change over the time. Then acceleration of the system along the time changes. Then that means the mass under the acceleration produces the inertia force. This is another very important point to be noted in the dynamic analysis. Thus, this particular cantilever beam will have a mass, right? This structure having mass will produce the inertia force. That the inertia force produced only in the dynamic analysis but not in the static analysis. When you take a static analysis, this force is neglected. But whereas in dynamic analysis, this force is existing. Very important. Now then there is something called degrees of freedom. In the dynamic, degrees of freedom means the number of independent displacement components that must be considered to represent the effect of all significant inertia force structure. That means if I have a structure, let's say something like this, a water tank, right? This is my water tank. Now what is the direction of the vibration? This is very important. It is, here is said here, the significant inertia forces, right? The number of independent displacement components to be considered. Suppose this is my wind direction, so vibration is going to be only this direction, right? So only this direction my inertia force is going to act. So how many ways like that is the degrees of freedom? So if I have only interest of one direction, so my degrees of freedom is 1. Right? Now, depending upon the coordinate to describe the motion, that means my motion is only this horizontal from this, let us say this is my x-axis, vertical is y-axis, there is my z-axis. Right now I am interested only x-axis, that is what here. Depending upon the coordinate to describe the motion. So I am describing the motion in x direction. So 1 degree of freedom. If I have to describe the motion of this tank, water tank, in z direction also, it becomes a 2 degree freedom system. If I have to describe the motion in vertical also, it becomes 3 degree of freedom. Right? That's very important. It is not universally the same. So we can make the same structure considered to be 2 degree, a 3 degree of freedom, or any number of degrees of freedom. So now, according to the situation, according to the description of the motion of the system, the coordinate you consider, one can be a single degree freedom system. For example, I have same thing I mentioned you, a water tank, right? I consider this water tank assuming that wind load is this direction, x-axis my, let us say, coordinate direction. So I take this to be a single degree freedom system. Suppose the z-axis is weaker, let us say, then I consider another time design z coordinate, there's another degree of freedom, one at a time, right? Now, multi-degree freedom system, like if you look at a 3-story building, floor 1, floor 2 and floor 3. Each floor having mass 1, 2, 3, M1, M2, M3. Now, because of the lateral loads on each of the floors, so I can model it like this. This is called mathematical modeling of the building. So each of the building floor vibrating or moving motion in horizontal direction. So I am interested to know the coordinate of those floors in the horizontal direction. So this will be 1, 2 and 3. So this is 3-degree freedom. We call it as multi-degree freedom system, anything more than 2. Then there is another degree of freedom, we call it as continuous system, wherein the system we cannot say discretely this number of lumped mass. So like in a chimney, cooling towers. So this is a continuous mass. So this system is called continuous system. It will have infinite number of degrees of freedom. Right? So this is the degrees of freedom. Now if you take a single degree freedom system in detail, right, that means a single coordinate is sufficient to describe the position or a geometry of the mass, right. Then this mathematical modeling of this single degree freedom system. So this is a mass and moving in u direction, horizontal direction, with a displacement of u, x direction, x axis, and over the rollers. That means there is no friction, and having some resistance to motion by stiffness and resistance to motion by damping. Okay, so this is single degree freedom system, and this is an example of a table vibrator mounted on 4 springs, vertical motion of this. And another way of representing this single degree freedom system on as a mathematical modeling, like a spring of stiffness K having a mass of M and having a damping C and vibrating vertically. Suppose a system do not have a damping, can be represented mathematically like this: a spring with stiffness K, mass M, and when I give initial displacement, the system starts vibrating vertically. Okay. So this is how mathematically we can model the single degree freedom system. Now, how to model a multi-degree freedom system? First of all, the definition: if more than one coordinate are required to completely describe the position and geometry of the masses system. That means here, as I told you, the 3 stories. So we need one coordinate, one here, second coordinate here, third coordinate here. Only then I will know how is the motion, the position of each of the floor in horizontal direction at a given point of time. Very important. At any instant of time. Where are these floors at any instant of time? To tell, I need 3 degrees. So 1, 2, 3. So this is like a multi-degree freedom system. The mathematical modeling of this system is like this: from the floor, the first mass, second mass and third mass. So I am representing this 3-degree freedom system in axially, and my building is lateral. So that means my spring, what I am taking here, the spring is nothing but, this spring is nothing but my columns, nothing but my column with a lateral stiffness. Okay, lateral stiffness. Here springs have the axial stiffness. Okay, axial stiffness. And the columns have a damping, right? The columns have a damping C, and here I have a dashpot. That's all difference. Okay. Now that can be represented like this with a lateral stiffness of the first floor K1, K2, K3, and the columns have a material damping like C1, C2 and C3. So in the continuous system, So if the mass of system may be considered to be distributed over the entire length in which the mass is considered to have infinite degrees of freedom, also known as distributed system. Okay, so like a cantilever beam with a different loading like this, uniform triangular loading there, this part of that, right? So this vibration of this, so entire beam is divided into number of parts, and each part taken as one mass. Let's say mass 1, mass 2, mass 3, mass 4, so on up to n number, and that becomes n degrees of freedom. I can do more also, right? I can take a similarly separated beam, same thing, you can have a number of parts of this beam and infinite number of degrees of freedom I can consider. Same thing, cantilever due to self weight, same thing. And the same thing, an example of a chimney or cooling tower, right? So this is a continuous system. Now the next part is the elements dynamic system. So what is the dynamic system? That means the elements of the dynamic system are mass, we have stiffness K, then damping C. These are the fundamental elements of dynamic systems, without which we cannot describe the dynamic system. So what happens to this? The internal forces in the dynamic system is produced by the mass, which is called inertia force. Next, the stiffness force produced by the spring K, right? Then the damping dash part produces the damping force, and the inertia force is written as mx double dot. This is acceleration. This is acceleration, which is d square x by dt square. The stiffness force, which is k times x, stiffness times the displacement. Damping force, the damping coefficient times velocity. This is the internal force, right? Now the external force acting on the dynamic system is nothing but the applied force, which is F of t, is a time dependent force. Now if you look at this force displacement diagram here, so in the x axis I have displacement, velocity and acceleration, and the y axis respectively corresponding to displacement I have a stiffness force, corresponding to velocity I have a damping force, corresponding to acceleration I have inertia force, and all of these forces will have a linear representation. So if I have displacement versus spring force, I get a slope of the curve of the line, which is known as stiffness. The velocity versus damped force we call dash part or damping coefficient. The acceleration versus inertia force is a mass, right? So these are the elements of your dynamic system. These are to be determined. Okay. Now if I have a building system where the system is excited by the external force F of t, right, at any point, maybe in the at the top or could be at the bottom, anywhere, then this system, which is the building, the response can be measured as the displacement x of t, or velocity x dot, I call it as x dot means dx by dt, or you can say u of t. The acceleration, which is x double dot, that means d square x by dt square, which is a of t, right? So like this we can measure the response. Now when you look at the equilibrium of the system, so one equilibrium is a static equilibrium, which we already discussed. In the static equilibrium, we say if there is a system or a body subjected to external force, for example, F1 is a force acting here, the system will rotate. So I must have some equivalent force in its location such that the body does not rotate and the body does not have a translation. So that is F2, right? And anyway I don't have a lateral forces, so which body will not have a horizontal translation, right? That means I have three equilibrium equations: summation fx equal to 0, summation fy equal to 0, summation mz equal to 0. These are three equilibrium equations. Now when you speak to the dynamic equilibrium, what happens that a system subjected to the inertia forces, which is internal force, resisting to the external applied force, and the damping force, which is the coefficient, damping coefficient times velocity, the stiffness force, spring force, which is stiffness coefficient times displacement, right? These are internal force or resisting force. The external force acting on that is F of t. When these two are same, then we call it the system in the dynamic equilibrium, right? It's quite different what we discussed so far, right? When system is in equilibrium, that means inertia force, damping force and stiffness force is equivalent to the external force. Okay, so that I can represent in the form of a system like this. Inertia force is opposite to the motion, right? Then stiffness force also the opposes the motion, and damping force, the external force carries the system, right? This is what dynamic equilibrium all about. Thank you.